Good morning, students. So today I will start organic chemistry. Some basic concepts in organic chemistry. Okay. Now in this chapter, we'll discuss some basic concepts in chemistry, especially in organic chemistry. So we know that organic chemistry is all about compounds containing carbon. So what is that versatile nature of carbon? So why carbon is involved in almost all organic compounds? So that is because of tetravalency of carbon, catenation ability. Catenation means the ability to form long chains. Ability to form long chains. Next, high bond energy means to break a bond between carbon and carbon, we need very high energy. That means CC bond is very stable. What does that mean? CC bond is very stable. This is why carbon is able to form millions of organic compounds. Then, types of hybridization. Types of hybridization. If carbon is involved with C single bond C, then carbon is said to be sp3, double bond, sp2, triple bond, sp. If carbon is attached on both sides, double bond. Here, this is also sp. Here, this carbon is attached with double bond, sp2. This is sp2. Now, this is regarding types of hybridization. Next, based on hybridization, we have one more model, that is calculation of hybrid and pure orbitals. Calculation of hybrid and pure orbitals. How we can calculate hybrid and pure orbitals in any given compound? Let us suppose if you consider, I'll give you an example. Let us start with one simple example. Methane, CH4. Now in this carbon, we know that sp3 hybridized. That means total, how many hybrid orbitals are there? 1s and 3p. Total 4 hybrid orbitals. Whereas there are 4 hydrogen atoms. 4 hydrogen atoms produce s orbital. So these s orbitals are not hybridized. They are pure orbitals, right? So 4 hydrogens have 4 s orbitals. These are pure. So hybrid is to pure orbitals. What is that ratio? Hybrid 4, pure also 4. That is 1:1 ratio. Okay. Similarly, if you consider CH3 single bond, CH3 ethane. Here also carbon is sp3 hybridized, this carbon is sp3 hybridized. So here carbon produce 4 hybrid orbitals. Here also carbon produce 4 hybrid orbitals. So total hybrid orbitals 8. Then if you consider hydrogens, here you can see here 3 hydrogens, here 3 hydrogens. All 6 hydrogens are producing 6 orbitals, 6 s orbitals, pure s orbitals. So 6 pure s orbitals. So hybrid is to pure. Hybrid 4 plus 4, 8, pure 6. That means 4:3 ratio. Next. CH2 double bond, CH2. How you can calculate here? Here carbon it is sp2 hybridized. Here sp2 hybridized. Total now how many hybrid orbitals here? Here 3, here 3. So hybrid. Total 3 plus 3, 6. But actually carbon, how many orbitals it will have? 4. 4 means out of 6, 4, 3 are hybridized, right? Carbon will have 4 orbitals. Out of 4, 3 are sp2 hybridized. That means 1 orbital is pure. Understood? So each carbon is having 1 pure orbital. So 2 carbon atoms are there. So 2 carbons will give you 2 pure orbitals. Okay. Then hydrogens total 4. 4 hydrogens will give you 4 pure orbitals. So total how many pure orbitals? Now it is a total of pure orbitals now. 2 from carbon and 4 from hydrogen. Total 6 pure orbitals. Similarly, total hybrid orbitals. How many are there? Hybrid orbitals here. 6. So as usual, hybrid is to pure. What is that? Hybrid 6, pure also 6. So here also it is 1:1. Similarly, if you consider one more example, CH3, CH double bond, CH2. Okay. Then how can you determine hybrid and pure orbitals here in this case? First, write what is the type of hybridization here. This is sp3. This is sp2. This is sp2. Now write down. sp3 means 4 hybrid orbitals. Here sp2 means 3 hybrid orbitals. Here it is 3 hybrid orbitals. So carbon, as I said, it will have 4 hybrid orbitals. Out of 4, if it is sp2, 3 are hybridized. That means 1 is pure here and 1 is pure here. And always consider number of hydrogens as pure orbitals. How many number of hydrogens are there? Here 3, 1, 2. Total 3 plus 1, 4, 4 plus 2, 6. Hydrogens will give you 6 pure orbitals. Now calculate total now. Calculate total. Total hybrid orbitals. How many are there? 4 plus 3 plus 3. 6 plus 4, 10. total pure orbitals. How many? 1 from each carbon, that means 2, and 6 from hydrogen. So 2 plus 6, 8. Therefore, hybrid versus pure, 10:8. What you can say? 5:4. So this is how you should calculate ratio of pure and hybrid orbitals. Ratio of pure and hybrid orbitals. Done. Next, we'll move to another topic, Iupac nomenclature. So I think you know what is Iupac nomenclature. Right. So how we'll proceed? Iupac nomenclature, root word followed by primary suffix followed by secondary suffix, which is followed by primary prefix, and this is secondary prefix. Right? Root word gives you number of carbon atoms in the longest carbon chain. Number of carbon atoms in the longest carbon chain. Primary suffix give you whether the compound is saturated or unsaturated. If it is saturated, that means C single bond C. Then you should use A. Unsaturated means C double bond C. Then you should use E. C triple bond C. Then you should use I. Whereas secondary suffix gives you main functional group. It indicates main function. Here, primary suffix indicates cyclic nature. If the given compound is cyclic, you just add cyclo. Then here, secondary prefix. Secondary prefix indicates other functional groups or substituents. So this is about Iupac. Let us consider some examples. CH3, CH2, CH2, CH3. So give numbering 1, 2, 3, 4. 4 means bute. All are single bonds you can see. A. There is no other functional group, just end with E. So what is its name? Butane. Or CH3, CH, CH3, CH2, CH3. 1, 2, 3, 4. Second carbon is having methyl. So what will be its name? 2-methyl. How many carbons? 4. So butane. If you include a functional group, CH2, CH, CO, CH3. 1, 2, 3, 4. Bute. All are single bonds. Ane. Second carbon, you are having ketone, 2O. Or simply you can write 2-butanone. So this is how you should write a Iupac nomenclature. Done. Next. Isomerism. What is isomerism? Compounds having same molecular formula but differing physical and chemical properties. So there are two types of isomerism. In the first one, structural isomerism. In structural isomerism, we'll see first one, chain isomerism. What is chain isomerism? Compounds having same molecular formula but differ in carbon chain. Examples, if you take CH3, CH2, CH2, CH3. What is this molecular formula? C4H10. Same compound we can write as like this. So the change in carbon chain. Second, change in position of functional group. C4H10O. So functional group is presented first carbon. So it will be one butanol. But same compound with same molecular formula can be written as like this. 1, 2, 3, 4. So this is what we call butanol. Now what happened here? Changing position of functional group. This here functional group is presented first carbon. Here functional group presented second carbon. Third one. Functional group isomer. Change in functional group itself. Again, I'm considering same molecular formula. So let us consider CH3, CH2. What is it? One butanol. The same molecular formula, I can write this compound like this. What is this? ROR, ether. What is it? Diethyl ether. So, same molecular formula, one compound, we are showing it as alcohol. With same molecular formula, second compound is diethyl ether. So, there is change in functional group. Okay. Next. Metabolism. What is metabolism? So this is different. Compounds having same molecular formula but differing attachment of alkyl groups to the same functional group. Functional group should not change. Example, now here, what is this alkyl group? Ethyl. What is this alkyl group? Ethyl. Right? Both are ethyl groups only. So both are ethyl groups means with another molecular, another structure I am writing here. Here, what is this? Propyl. Here, this is methyl. Now, what happened here? There is change in attachment of alkyl groups. Here it is, you can see, this is ethyl group, right? And here it is a methyl group. Change in alkyl group. Here it is ethyl. Here it is propyl. Again, change in alkyl group. Attachment of alkyl group changes, but same functional group. Here it is either, it is also either. So that is what we call metabolism. Next, tautomerism. What is tautomerism? It arises due to transfer of proton from one atom to another. How? Okay, let us consider acetone. Okay, now oxygen gets negative charge, immediately it will take up this H plus. Immediately it will take up that H plus. Then what will happen? CH3, C. Now this will become OH. Here we are getting a double bond. Right? This is enol. This is keto form. So this is what we call keto enol catamorism. Very simple thing. Very simple thing. It is a transfer of keto enol catamorism. Simple method, simple mechanism, that is transfer of proton from one atom to another atom. Here, proton is transferred from carbon to oxygen. Proton is transferred from carbon to oxygen. So this is a catamorism. Last type, ring chain isomerism. So what is ring chain isomerism? So what is this? Propane. What is molecular formula? C3H6, isn't it? Then same compound we can write like this. Now this is a cyclopropane. So this is a chain form, open chain. This is a ring form. The same molecular formula. Same molecular formula, we can write open chain compound, at the same time closed chain compound, that is ring. So this is what we call ring chain isomerism. Next type, stereoisomerism. So stereoisomerism again is divided into two more types. What is that? Geometrical isomerism. What is geometrical isomerism? This is due to restricted rotation of C double bond C. Why we are having geometrical isomerism? Due to restricted rotation of C double bond C. We cannot rotate a double bond between two carbon atoms. So due to this, we have different types of isomers. In that first one, cis-trans isomerism. So what is that? Let us consider one simple example, 2-butane. Okay. So I'm considering here cis-trans isomers. What is that example? 2-butane. Is that example we are considering here? 2-butane, right? So let us see 2-butane. What is 2-butane? CH3, CH, double bond CH, CH3. First, consider it the C double bond C, C double bond C. Now here you can see this carbon is having two substituents. What are they? One hydrogen and one methyl group. So write down those two. Hydrogen, methyl. This carbon is also having hydrogen and methyl. So this is hydrogen, this is methyl. Now, same groups are present on same side of the double bond. Both methyl groups are present below the double bond. So this is what we call cis 2-butane. If same groups are present on the same side of the double bond, then it is called cis isomer. When you consider opposite, H here, CH3 here, CH3 here, H here. Now you can clearly see the two groups, same groups are present across the double bond. That means opposite sides of the double bond. Then it is called a trans 2-butane. Understood? Then this is our cis trans isomerism. EZ configuration. What is EZ configuration? You take C double bond C. Okay. Fluorine, chlorine, bromine, iodine. So how to represent EZ notation? Very simple. Give priority order. Only one rule, sir. Arrange the atoms or group of atoms attached to double bonded carbon based on atomic numbers. That's it, sir. Then can you arrange? Based on atomic numbers, chlorine is highest atomic number. Fluorine is second highest. So between chlorine, fluorine, chlorine will get highest priority. Fluorine will get second priority. Right. Similarly here between bromine and iodine. Between bromine and iodine, iodine is having more atomic number. So it will get first priority and bromine will get second priority. See here, if same priority groups are present on the same side of the double bond, here first priority, here first priority, both are present below the double bond. So such an isomer is called Z isomer. If same priority, here also give priority, chlorine first priority, chlorine 2, here this is iodine first priority, this is second priority. Now, first priority groups, you can see they are present opposite sides of the double bond. Then it is called E isomer. Then it is called E isomer. So this is about EZ configuration. Then optical isomerism. What is optical isomerism? So you can consider optical isomerism two conditions. What are those two conditions? At least one chiral carbon should be there. What is chiral carbon? Carbon having 4 different substituents. Carbon having 4 different substituents. That is what we call chiral carbon. Next, the compound should be able to rotate plane polarized light. The compound should be able to rotate plane polarized light. So, if any compound is satisfying these two conditions, then it is said to be optically active. Then types. Enantiomers. Enantiomer means the 2 isomers should be mirror images and they should be non-superimposable. Next, diastereomers. What are diastereomers? Isomers should be they should not be mirror images, but non-superimposable. Second condition is same. The only difference between enantiomers and diastereomers is diastereomers should not be mirror images. So this is about isomerism. Then we move to the next concept. Electron migration effects. So in the first one, inductive effect. What is inductive effect? Delocalization of sigma electrons due to presence of electron withdrawing groups or electron donating groups. If electron donating groups are present, that means C, X. Now let us suppose this X is electron donating. What it will do? It will donate electrons into the carbon chain. So electron density is increased in the carbon chain. This is what we call plus psi effect. So this is directly related with electron donating groups. What are electron donating groups? Alkyl group, amine group, methoxy, OR. All these are electron donating groups. Next. If it is electron withdrawing group, what it will do? It will move that delocalization of sigma electrons away from the carbon chain. This is what we call minus psi effect. Then what about electron withdrawing groups? COOH, COR, COCl. SO3H, halogens. These are all electron withdrawing groups. So this is about inductive effect. Next. Electromagnetic effect. Delocalization of pi electrons here in the presence of an attacking reagent. it should be an attacking reaction. Let us suppose C double bond C H plus. This attacking reagent H plus. What happens? These 5 electrons will be shifted to the carbon. Then immediately this carbon will take up that proton. Then what is happening? This is forming a bond with hydrogen. Carbon gets a positive charge. So in this case, this is what we call plus C effect, or C double bond C nucleophile. What happens? This nucleophile it attack on this carbon, and what you'll get CN here, C. Now this carbon gets negative charge. This is what we call minus C effect. So this is a delocalization of pi electrons. I'll add one more point here. Inductive effect. It is permanent effect. Whereas electromeric is, it is temporary effect. Done. Next, mesomeric effect. What is mesomeric effect? So, electromeric effect is a complete transfer of pi electrons. Complete transfer of pi electrons. But here, mesomeric effect, it is a polarity produced in the molecule by the interaction of two pi bonds, or between a pi bond and lone pair present on adjacent atom. Present on adjacent atom, right? Again, here also same. If you consider plus M effect, minus M effect, let us suppose plus M effect. What we'll consider? Positive inductive effect, positive electromeric effect, all these are CH2 double bond, CH, Cl. Chlorine is having lone pair, so this lone pair will come here. It's interaction between lone pair and pi electrons. Lone pair and pi electrons, right? Minus M effect. Let us suppose H double bond CH and double bond O. Nitro group is attached to that. And what will happen? These electrons will come here, these electrons. So interaction between two pi bonds. Interaction between, in this case, two pi bonds, right? Next effect, resonance effect. Next is resonance effect. So what is resonance effect? If the properties of a compound cannot be explained by a single structure, we'll propose two or more different structures, right? So this looks similar to mesomeric effect. It looks similar to mesomeric effect. Okay. But here, the difference between if there is a conjugation of two pi bonds, that means alternative pi bonds. That means double bond, single bond, double bond, single bonds. Then electrons of one pi bond would be transferred to the other bond. Similarly, if there is a conjugation of one negative charge or a lone pair of electrons and one pi bond, then there will be again shifting of electrons from lone pair to bond pair or bond pair to lone pair. So this we can explain plus R effect. Consider OH. So oxygen is having lone pair. This lone pair will come into the resonance. Minus R effect. Consider nitrobenzene and double bond O. What will happen? These pi electrons coming here, these pi electrons are shifted to carbon. Then what you will get here? You will get positive charge, double bond, NO minus. So this is what we call plus R and minus R. Plus R, so is due to the presence of electron donating groups. Minus R is due to the presence of electron withdrawing groups, right? This is about electron migration effects. Now let us see some questions remaining purification methods, qualitative analysis, quantitative analysis. That is completely theory part. So if possible, just go through the textbook. Meanwhile, we'll solve some questions. So always, when it comes to organic chemistry, there should be one question based on nomenclature. So no doubt there will be one question based on nomenclature always. So you should have clear idea about nomenclature. So let us see. Let's solve some questions. The number of sigma and the pi bonds in pent to in 4 ine is. Options given are 13 sigma and no pi bond, 10 sigma and 3 pi bonds, 8 sigma and 5 pi bonds. Fourth option, 11 sigma and 2 pi bonds. Can you find? We need number of sigma and pi bonds. How can you do it? First, draw its structure. Pent. Pent means how many carbons? 1, 2, 3, 4, 5. So let us give numbering first. 1, 2, 3, 4, 5. According to the given 2 in, second carbon is having double bond. This is 4, right? 4 ine. Fourth carbon is having a triple bond. 1. Now satisfy with hydrogens. How? This carbon is having only, first carbon is having only one bond. That means remaining 3 will be hydrogens. This carbon, 1, 2, 3, total 3 bonds are there. So 1 hydrogen. This carbon is also having 3 bonds. So this carbon having 4, no need to add hydrogens. Last carbon is having 3 bonds. So add 1 hydrogen. That's it. Now, for your understanding, I am writing like this. First carbon, H, H, H. Second carbon, H, double bond, C, H, C, triple bond, C, H, right? Now it is easy for us. This is sigma, this is sigma, this is sigma, sigma, sigma. So 1 sigma and 1 pi bond. This is sigma, sigma. First bond will be sigma, then how many bonds will be there? All they are called pi bonds. So this is sigma. Now calculate how many sigma bonds are there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many sigma bonds, sir? 10 sigma bonds, and pi bonds you calculate. How many pi bonds here? 1, here 1 pi bond, here 2 pi bonds. So total 3 pi bonds. So 10 sigma bonds and 3 pi bonds. So this is your answer. Which option? 10 sigma and 3 pi bonds. Second option. Okay. So one more question we'll see. Which of the following molecules represents the order of hybridization? sp2, sp2, sp, sp, from left to right atoms. Direction also given. Options are CH, triple bond, C, single bond C, triple bond CH. This is first option, sir. Second option, CH double bond CH, C triple bond CH. Third option, CH2 double bond CH, CH double bond CH. Last option, CH3, CH double bond CH, CH3. This is the last option. Let us see. This carbon is attached to triple bond. Triple bond attached sp, left to right, sir. We have to move from left to right. Then this is also sp. This is sp. This is sp. So all are sp. But the order is sp2, sp2, sp, sp. So ruled out. Next, this is sp2 attached to double bond. This is also attached to double bond. This is sp, because this is attached to triple bond. Last carbon is also attached to triple bond. So sp2, sp2, sp, sp. Correct. Did you understand? So from left to right, this order should be there. So which is satisfied by the second compound. Okay. Shall we move to one more example? Next question, question number 3. the state of hybridization of C2, C3, C5 and C6 of the hydrocarbon. This is a given compound. CH3, C, CH3, CH3, CH, double bond, CH, CH, CH3, C, triple bond, CH. This is the given compound. Now give numbering. 1, 2, 3, 4, 5, 6, 7. And we need to identify a hybridization of which carbon atoms. Let us mark them first. C2, C3, C5 and C6. So let us proceed one by one. What is C2 hybridization? C2. It is attached to triple bond. Sp. Yes, CH. CH, the third carbon. All are single bonds, you can see there. All are single bonds means sp3. Fifth carbon is attached to double bond. sp2. Sixth carbon, you can see all are single bonds only. All are single bonds means sp3. Did you understand? So this is how you should write hybridization. Next question. The Cl-C-Cl angle in 1122 tetrachloroethane. 1122 tetrachloro and tetrachloromethane. So this is ethene. Just one correction. This is not ethane, ethene. This is methane. Okay. So please try to understand. I am specifically mentioning methane. Okay, two compounds are given. We need to find out bond angle. We need to find out bond angle. That's the question. So first take first compound. What is the first compound given there? 1122 tetrachloroethene. C double bond C. Fluorine here, fluorine here. Fluorine. Now the bond angle. What we need to find out? Bond angle. That means Cl-C-Cl. Cl-C-Cl. This is the bond angle we need to find out in this compound. Right? What is that bond angle? Here. This is all. What is hybridization here? sp2. sp2 hybridization. What is bond angle, sir? Simple, 120 degrees. So in this compound, the hybridization of carbon is sp2. So it is having a bond angle of 120 degrees. Second. What is second compound? Tetrachloromethane. That means tetrachloromethane. Now this is attached with only single bonds. That means what is bond angle? Hybridization sp3. In sp3, what is bond angle? 109 degrees, 28 minutes. So based on hybridization, you can easily determine bond angle. Done? Next compound, next question. Let us see Iupac names. Questions based on Iupac names. Question number 5. The Iupac name of the compound. The Iupac name of the compound. Now this is the compound given, sir. C double bond O H, CHO. CHO means aldehyde. Is options given are first option 5 formyl hex 2-ene 3-O. Try to find out. I'm giving you options 5-methyl 4-oxo hex 2-ene 5-ul. Next 3-keto 2-methyl hex 5-enol. Last option 3-keto 2-methyl hex 4-enol. 4-enol. So how you will name this? So always find out longest carbon chain. Okay. Now here, generally what we'll consider, if any functional group is present at terminal position, functional group having carbon is present in terminal position, then you give numbering from that carbon. There is one rule, right? But in the given compound, in which direction we should give numbering? Okay. See where the functional group having carbon is present at terminal position. Let us start give numbering from that carbon. So this is 1, 2, 3, 4, 5, 6. Total 6. For this, what will be the root word? Hex. Okay. At 4th carbon, we are having ene. 4-ene. Main functional group, what we are considering here? CHO. CHO means ul. So hex 4-enol. Then remaining will become substituents. What are substituents present? Yes, second carbon is having, this carbon is having methyl group here, right? This is methyl group. If nothing is given, means that is methyl. And third carbon, you are having the keto. So methyl and keto, alphabetical order. Who will come first? Keto. So that means the third carbon you are having 3-keto, and the second carbon you are having the methyl. So 3-keto, 2-methyl hex 4-enol. Which option, sir? Fourth option. Right? Then we'll proceed with one more question based on Iupac nomenclature only. The correct Iupac name. One more question, sir. For the compound, what is that? This is the compound given, sir. Double. Whenever you will find a double bond, give priority to that double bond, right? Easy to remember. So here it is double bond. 1, 2, 3, 4, 5, 6. So start giving them name of this compound. So you can clearly see there what is root word? Hex. Double bond is present at first carbon. 1 ene. There is no other functional group end with ene. Then substituents will proceed. Okay. Now this third carbon is having what type of group this is? This is 1 carbon, 2, 3. That means third carbon is having propyl. Here you can see fourth carbon. Next, fourth carbon is having 1, 2. Fourth carbon is having ethyl. Right. Third carbon is having propyl. Fourth carbon is having ethyl. Then what we can say? Ethyl propyl, priority alphabetical order. Ethyl will come first. That means 4 ethyl, 3 propyl. Hex 1 ene. So 4 ethyl, 3 propyl, hex 1 ene. Okay, we'll see one more compound. Again, Iupac name of is the compound so always identify functional group. This is the functional group COCl. COCl means oil chloride. This is Iupac name. COCl means oil chloride, right? So give numbering as usual. We proceed with same style. So carbon, functional group carbon 1, 2, 3, 4, 5. Okay. So all are single bonds. Pent. All are single bonds means ane. What is functional group? Oil chloride. So what it will become? Pentanoyl chloride. Then substituents. Second carbon you can see is having methyl group. Third carbon is also having methyl groups. That means 2, 3 dimethyl pentanoyl chloride. 2, 3 dimethyl pentanoyl chloride. Okay. We'll see one more question, then we'll move to next model. CH3, CH double bond, CH, CH2, CH, NH2, CH2, COH. Now, whenever you'll find carboxylic acid, the task will become easy. The reason is give numbering from the COOH group. 1, 2, 3, 4, 5, 6, 7. That's it. Now, third carbon having substituent, that is amino. Fifth carbon is having double bond, ene. That's it. You just give numbering. How many total carbons? 7. That means hept. Fifth carbon is having ene. First carbon, oic acid. And prefixes. Only one substituent is there. That is 3 amino. 3 amino. Right? Or simply what we can write, 3 amino, 5 heptene oic acid, heptenoic acid. Okay. Next question, we'll move to isomerism questions. The compound which shows metamerism is, options given are C4H10O, C5H12, C3H8O, and last option C3H6O. Let us consider first option, C4H10O, whether it exhibits metamerism or not. CH3, CH2O, CH2, CH3, or CH3O. So this is ethyl, ethyl. This is methyl, propyl. So there is change in difference, change in attachment of alkyl groups to the same functional group. So these two are called metamers. So first compound, first molecular formula itself exhibits metamerism. Done. Okay, shall we proceed for next question? So question number 10, the number of isomers, in C4H10O will be, options given us 7, 8, 5, 6. Let us consider that molecular formula C4H10O. So what we can write, CH3, CH2, CH2, CH2OH. This is 1 butanol. Next, CH3, CH, OH. This is why it is 1-butanol. OH is presented first carbon. Here 1, 2, 3, 4. This is 2-butanol, which is presented second carbon. Next, CH3, C, CH3, CH3, OH. 1, 2, 3. 2-methyl. To propanol. Then CH3, OH, CH2, it's not, sorry. Write ethers for that molecular formula. How many ethers you will get? What is this? 2-methyl, 1-propanol. So total how many alcohols we are getting there? 4. How many, sir? 4. That is right, ethers for that. CH3, CH2O, CH2, CH3. CH3O, CH2. There's one more ether. Isopropyl group, sir. This is one more. So total 3 ethers. Here total 4 alcohols. So total 3 plus 4. Total isomers will be 7. Total isomers will be 7, right? So this is how you can calculate the number of isomers for a given molecular formula. Okay. Next. Question number 11. Which of the following statements is not correct? Is not correct for a nucleophile. Options are ammonia is a nucleophile. Next, nucleophiles attack low electron density sites. Next, nucleophiles are not electron seeking. Last one, nucleophile is a Lewis acid. And what is general statement regarding nucleophile? Nucleophile is electron rich. Okay, if it is electron rich, ammonia, nitrogen is having a lone pair. Ammonia is having a lone pair. So it is electron rich. Correct. Nucleophile attack low electron density sites. Low electron density means electron deficient. Nucleophile is electron rich. So definitely it will attack the electron deficient sites. That is also correct. Nucleophiles are not electron seeking. So there is no need of electrons for nucleophiles because already they are electron rich. So they are not electron seeking. That is also correct. Nucleophile is a Lewis acid. Actually, what is Lewis acid? Lewis acid is electron pair acceptor. So you can accept electron pair, but nucleophile is electron rich. So there is no need to accept electrons. Always it donates electrons. So this is a wrong statement. It is not Lewis acid, it is a Lewis base. It is Lewis base. Next, question number 12. Which amongst the following is the most stable carbocation? Options are CH3 plus, CH3, CH2 plus, CH3, CH, CH3. So what is order of stability of carbocations? Order of stability of carbocations. What is that order? Tertiary carbocation is more stable than secondary than primary. And last one, methyl carbocation. Before this, we have allyl carbocation, and it is less stable than benzyl carbocation. Benzyl carbocation is having resonance, that is, it is more stable, right? Now, among these, this is methyl. You can see here, methyl is least stable. Next, this is this carbon is attached to one carbon, so primary carbocation. Now, this carbon is attached to two other carbon atoms. This carbon is attached to total how many? 3. So this is so we have methyl 1 degree, 2 degree, and 3 degree carbocation. So definitely tertiary is more stable than secondary, primary, and methyl. So more stable carbocation is tertiary carbocation. Tertiary carbocation. Okay, so this is about first chapter in organic chemistry. Then we have second chapter, that is hydrocarbons. That is hydrocarbons, right? So that we'll see in tomorrow's session. Okay. So have a nice day then.